Before we go to the next step, we need to define mu and sigma, mutation rate and step size of the mutation, and I'm going to define them here after the gamma. Mu equals to params dot mu, and also sigma equals to params dot sigma. And also need to define this in app.py, the starting script, and params.mu will be, for example, 20%. And that's why we have 5 decision variables here, and setting mu to be 20%. Then in average, we're going to modify or alter one of genes every time we're going to perform mutation. If you want, you can, for example, set this to 10%, and that's we're going to change a half of a gene every time we're going to perform mutation. And also I'm going to define the sigma here, and sigma will be equal to 0.1, and that's fine, I think. And now we're ready to evaluate these solutions. But before that, we must ensure that the positions of our offsprings are in the range. The positions must be greater than var mean and less than var max. So we must ensure that the values are in this valid range. So I'm going to apply bounds to these positions, and to do so I'm going to define another function here, def apply bounds, and it accepts a single individual named x, for example, and we must provide var mean and var max too. And I'm going to compare the position of x to var mean and var max. So np.maximum returns the maximum value among 2 arrays or numbers, and I'm going to pass x.position into this function, and also var mean. Normally, position of our individuals should be greater than var mean, and if we have a normal position here, then the result of this expression, finding maximum among this value and this value, will be position. In case of any invalid value, then position will be less than var mean, and that's not valid, but the maximum will return var mean as output. So definitely the output, the result of this expression, will always be greater than or equal to var mean. So I'm going to use this as x.position, the new position of x. If everything is okay, then x.position will be equal to itself. And if there is some invalid members in the position, then those elements will be replaced by var mean, and we will have var mean as positions at those indices for those genes. Let's copy this and change it to have the var max in a similar way. We change the maximum to minimum and var mean to var max, and normally the position should be less than var max, and in case of any invalid value, then the output of minimum will be var max. So this expression will always be less than or equal to var max. So that's it. And we know that x is a reference type and has a reference type structure, and any change in its fields will be reflected everywhere. So there's no need to return anything, but if you wish, you can return x as well. I'm going to call apply bounds here. Apply bounds c1, the first offspring, and var mean and var max. And also we're going to apply this to c2 as well. And that's it. We applied the bounds, lower bound and upper bound of decision variables, and now we are ready to evaluate the solutions. To evaluate the solutions, I'm going to evaluate first offspring. I'm going to set the cost of c1 equal to cost function at c1 dot position, and also I'm going to compare c1 dot cost to best sold.cost. So if c1.cost is less than best sold.cost, then similar to the initialization part of our code, best sold must be replaced by c1. But we can not do this assignment because we're dealing with reference type variables. Structures are reference type. So c1 dot deep copy actually will be replaced best sold to ensure that any changes in c1 in future will not affect best sold. So we evaluated the solution and we updated the best sold as well. And I'm going to copy this part and do the same for second offspring. I'm going to replace c1 with c2, and here we evaluated two newly created solutions which are a result of mutation after a crossover. So that's it, we evaluated the solutions as well. However, we're going to add them to popc. So let's add offsprings to population. I'm going to popc.append c1 and also append c2, and that's it. We now have a population of offsprings named popc, which contains nc individuals in that. And here you see that k is not used at all. We can replace this with an underscore, a dummy variable name, and now we're ready to merge populations and sort and select the population for the next generation. Okay, let's perform the merging, sorting, and selection part of code. So I'm going to add a new section here, merge, sort, and select. So to merge two populations, we're going to use this operator, pop plus popc, and I'm going to assign this to pop itself. And you know that you can change this expression by removing pop plus from here and using plus equals operator, which is actually means we're adding popc to pop. We're merging them and we are naming the merged list as pop. Now we're ready to sort the population. So let's sort the population using sorted function, and sorted accepts the list population, and we must provide a key to use as the criterion to sort, to compare members or individuals of the population. So I'm going to define key equal to, we're going to define an anonymous function, a lambda function here. So I'm going to define a lambda function which maps x to x.cost. So we're telling that the key of this sorting operation is an anonymous function which returns x.cost for any x in the population. And that's, we're using x.cost, the cost value, as the key value to sort population. And that's it. We sorted the population by this key value. However, we need to store this in pop. So this will not change the population, and we need to store this in pop. And now we have a sorted, merged population, and we're going to select the top members as new population, the population for next generation. So pop equals to pop from the first of list, from the index 0 up to n pop. And actually we know that this will contain 0 to m pop minus 1, and we will have m pop members of the population, of the sorted merged population here. And we're done. We successfully implemented merge, sort, and select here. And now we can continue with the implementation by storing the best cost found at the end of this iteration. So store best cost pure. We have best cost of this iteration equal to best sold dot cost. We're going to print some information about the iteration, show information show iteration information actually, and we're going to use the print command, which accepts a string, iteration, a number as a parameter, and best cost equals to this dot format, and we're using it as first parameter and best cost at it in this place. So iteration and best cost iteration, or simply you can use best sold.cost if you wish, and that will be fine. So this is the information about iteration being shown by this print command. And I think we've done. We implemented the genetic algorithm, we extract the problem information, parameters, and we created an initial population, and then we performed parent selection, crossover, mutation, we applied bounds, we evaluated newly created solutions, and finally we merged and we sorted the population. However, we have a mismatching of loops here. This is inside this loop, so we must have them outside of this loop, and we have this loop for crossover and creating POP-C, but this loop is for iteration, and these lines must be out of this inner loop here. So that's it. And finally, we store the best cost value and show some information about iteration. And after the execution of algorithm, after exiting this for the main loop and outside this loop, we have output, which returns population, and I'm going to return best sold, and also I'm going to return best cost. And that's it. This will encapsulate population, the final population, the best solution ever found, and the track of best cost at the end of each iteration, and it will return them as a single structure here. And I think we've done. Let's check for APP1. We have a fully functional genetic algorithm, and now we're ready to see how this script works. So let's run this by hitting F5 and running Python file. Okay, we have an error message here, and I think NC is of type numpy float 64, and NC is the result of calling the mp.round. So I'm going to convert this to integer by casting it, and I think this will resolve the problem. And so let's run the code, and you see that we have the results here. From the iteration 0 has the almost 40 as the best cost. We have 7.3 times by 10 to the power of -6. It's a really small number, and you see that genetic algorithm works. And you can change, for example, the number of iterations here, and increase the number of individuals we have to run the program, and you see the algorithm stocked here, but we can change, for example, gamma, mu, or other things to make the algorithm even better. For example, let's lower the mutation rate and set it to 1%, and let's check for this. For this specific algorithm, it didn't change the result, but we can increase the number of population, we can change any of these parameters to have better results at all. But we're going to change the way we have gamma in this code later, and to have high exploration level at the start of algorithm, and then decrease the level of exploration as we go forward. And to do so, we need to have two values for gamma, an initial value and a final value, and then we will change the gamma as we go forward. Okay, we're ready to add plots to this program, and I'm going to plot best costs inside a graph using the best costs as the data for y-axis and using the index or number of iterations as the horizontal axis. And to do so, I'm going to create a plot, and plot out.bestCost, and this will work fine. Let's decrease the number of iterations here. And also I'm going to plot that set the x limit from 0 up to max it defined here, and I'm going to use params.maxit. And also let's set labels for y and x axes, and I'm going to set this plot x label equals to iterations, for example, and also plt.y label equals to best cost. And let's have a title to plot title, genetic algorithm, or simply GA. And I'm going to add grid to, we can set grid equal to true here, and let's show the plot as well. And if we run this code, we will get this plot, this figure, which shows that the cost reduced from about 15 to near 0. And also we can use the logarithmic scale for our plots in a y-axis. And to do so, we can change plot to semi-log y. Let's comment this line and replace plot with semi-log y. And this is similar to plot, but the y-axis uses logarithmic scaling, and the improvements of cost in some optimization problems will be more visible in using this function, using the logarithmic scale for y-axis. So let's run the code. And here we have the convergence plot, as the G progresses, and we have iterations from 0 up to 99, and it's reduced from somewhere between 10 and 100. It seems that it's about 30, I think. Yes, that's 36, and it's reduced from there to below 10 to the power of minus or -5, and that's it. It shows that GA works fine, and it can find the best solution for a sphere function. You can replace any other objective functions, and you can check for the efficiency of GA. And of course, you need to tune the parameters for GA. And the GA is not using the roulette wheel selection. Next, we're going to replace this random selection with roulette wheel, and this will improve the efficiency of GA as well. But you need to tune GA parameters for some kind of problems to make the results more promising. Okay, we're going to replace this part, this random selection scheme, with roulette wheel selection. Okay, to do so, to implement the roulette wheel selection, I'm going to start a new terminal here, and I'm going to enter IPython, the interactive Python mode, and let's import NumPy here, and let's define a vector of probabilities here, p mp.array. For example, the probabilities are proportional to 1, 2, 3, and 4, and you see that the sum of p equals to 10. We must normalize this, but it's not needed at all. We can handle this inside the roulette wheel selection, as we've done in MATLAB implementation 2. Okay, I'm going to create a random number, and I'm going to compare that random number to the cumulative sum of p. We've done this before for MATLAB, and we reviewed the roulette wheel selection, and we converted the rotation of this circle, which is divided by the probabilities defined by p, into a linear form. And you see that we opened the perimeter of this circle and created this line from 0 to 1, and these cutting points, these boundaries of area 1, 2, 3, and 4, denoted by numbers. And you see that these numbers, 0, 0.1, 0.3, 0.6, and 1, these four numbers are cumulative sum of our selection probabilities. So we have these probabilities here, and we form the cumulative sum of these numbers, and then we create just a random number here, for example 0.32, and we find those values which are greater than this, and here C3 and C4 are found by comparing this with 4 of these values, and the first winner is the winner of the roulette wheel selection, and it's equivalent to rotating this circle and finding the section which is declared as the winner by this indicator, for example. And here I'm going to do same, and you can use mp.comSum to calculate the cumulative sum of p. So you'll get this 1, 3, 6, and 10. This is the cumulative sum of original array, and I'm going to create a random number, for example mp.random.rand, but we must multiply this by sum of p, so sum of p, and you get this. And 1.29 is less than these 3 values, so these are the potential winners, but we choose the first one as the winner of roulette wheel selection. So we have this here, and we're going to compare this with, for example, mp.comSum of p, and you'll get an array of trues and falses. If you run this command again, you'll get another array of true and falses. Here 4 of choices are potential winners, but we choose this as the winner. But here these are 2 winners, and we choose this as the winner, the first one. And if you run this again and again, you always get an array of trues and falses. However, I'm going to find where this array is true. So to do this, I'm going to pass this to argvar, mp.argvar, and this returns an array of indices. And if I call this again and again, you will get, for example, here 3 only, 1, 2, 3, 1, 2, 3, 0, 1, 2, 3, 3 only, and if you run this, you'll get 4 choices. For example, 4 cases, we get as the output 2, 3, 1, 2, 3, 0, 1, 2, 3, and 3 lonely. And if we see the result, it is an array and it contains a column. And to reach the first one, for example, you assign int to the output of this expression and you'll get this. And if you call for int, if you want to get that 3, you must get the first member, and the first member also is an array. So you must get the first member of this matrix because it is a 2-dimensional array, and that's 3. So the first member of this result is indicated by this. So we're going to use this in our implementation. Okay, I'm going to implement the roulette wheel selection here at the end of code. So def roulette wheel selection, and it accepts a vector or an array of probabilities denoted by p, and I'm going to create the comSum, calculate the comSum of this. C equals to mp.comSum of p, and also r equals to sum of p times mp.random.rand, and this is a number from 0 up to sum of p. And finally we're going to find indices where mp.arg where that r is less than or equal to c, and we're going to return int first member of first subarray. And that's it. That's the roulette wheel selection defined here. And we can use this inside our GA code here. And before doing this, we must calculate the probabilities as well. I'm going to calculate the probabilities here. Let's define the cost value for our population members. So we can denote this by costs, which is equal to a generative expression. This returns x.cost for x in pop. And this is a list of cost values of every x in our population. And that's it. Now we can calculate the average cost, AVG cost here. Similar to what we've done in MATLAB implementation, we're going to calculate the selection probabilities according to this rule. Selection probability in proportional to this amount, e to the power of negative beta times ci. Ci is the cost value and beta is the selection pressure. And we know that beta can be defined proportional to inverse of average cost, and generally we divide costs by average cost, but we take care of zero average, and we use beta, for example, as equal to 1 to whatever we want. The higher value results in higher probability for better members of the population, and the lower values near to close to 0 will result in more quality of selection of all individuals in the population. So I'm going to divide cost values by average value of costs. So this is costs, this is the average cost, and we can calculate mp.mean of costs, and if average cost is not equal to 0, then we can divide costs by average costs. But to perform calculations on this is a normal list, not a NumPy array. I'm going to use MP array to convert this to NumPy array, and I'm going to define costs equal to costs divided by average cost. And this is the normalization phase. And finally, props or selection probabilities are given by mp.exp e to the power of negative beta times costs. And that's it. We calculated the selection probabilities, and we must define beta as well. So let's have beta here after mpop. Beta equals to params.beta, and let's go inside app.py and have params.beta, the selection pressure, equal to 1. And here we have props, and I'm going to remove these parts and replace them with selection rule of roulette wheel. So I'm going to perform roulette wheel selection. Similar to this, P1 will be equal to pop, which element the roulette wheel selection, which accepts props as probabilities, and for the second parent we have the same. And finally we can remove this part. I'm just going to keep this as comments here. If you want, you can switch to random selection 2, and we have P1 and P2 here selected by roulette wheel selection. And let's run the code to see it's working. So I'm going to run this. Finally we have the result here, and is the result, and it's reduced to below 10 to the power of negative 11, you see, and that's working, and that's fine. And I think we have a working GA, and we're done with this implementation. You can modify, for example, this solution structure. You can modify the parameters, the problem, and you're free. And I think if you're familiar with Python and with concepts of optimization, you can use this basic code to solve even complicated and complex problems. And it's just needed to be justified and to be adapted with the structure and with the definition of your optimization problems. For example, if you want to use different ranges for your decision variables, similar to MATLAB, for example, we have 5 decision variables here, and we've done this in MATLAB too. Let's have different lower bounds and upper bounds for our decision variables. Let's assume that the first decision variable is from -10 to 10. The second one is also from -10 to 10, and the third one is from -1 to 1, and also we have -5 to 5, and final one from 4 to, for example, 10. And let's use these values as our lower bounds and upper bounds. Remember that if you're going to use different values for lower bound and upper bounds of variables, then the number of elements in this list, array, matrix, whatever you use, must be equal to this number. For example, if you want to set 10 for upper bound, it's okay. You can use a single number. But if you're using a list, the number of elements in the list must be equal to this. It's same for Python and MATLAB. You have to stay in this way and use either scalars as upper bounds, or if you're using matrices and arrays, then the numbers should match. Okay, let's run this example, and you see that 4 will be the best value of fifth decision variable here, and for others 0 will be the best. So 16 will be the best value of our objective function. So let's run the code and see what we get, and you see that it converges to 16, and this is the result we have. And you see it's okay, it's working. And if you want, you can, for example, for this problem, this specific problem, you can use plot instead of semi-log y. And if you run this, you will get a similar plot here. It reduces from about 26 to 16. And if you want, you can, for example, check for the results, the position, the cost value, whatever you want. It's available here, inside out, inside this variable. Okay, we've implemented genetic algorithm, the real coded genetic algorithm in Python, and you can implement binary genetic algorithm in a similar way. For example, you can modify this and add binary operators to have the binary genetic algorithm to Python too. But these days, the binary coding is not so useful, and you can convert almost any type of decision variables, the permutation type, the allocation type, and many applied optimization problems into real coded variables. So the real coded genetic algorithm and other algorithms as well are very useful, and almost in every application, the only thing you need to have is a real coded optimization problem, and that will be enough, because you can convert any type of variable to real variable. Okay, I think we are done, and we are at the end of our video tutorial, and hope this was helpful for you. And in case of any questions, comments, or suggestions, please let us know on yarpes.com, YouTube, Udemy, wherever you're watching this video tutorial. And thank you for watching, and wish you the best.